Hello, everyone. My name is Martin, and I'm the Director of Marketing at Evolven, and your host for this session. So, I'm happy to have our Chief Data Scientist, Boshan Kaluja. Boshan has done a lot of research into artificial intelligence and intelligent systems, machine learning, predictive analytics, and anomaly detection. Prior to Evolven, Boshan served as a senior researcher in the Department of Intelligent Systems at the Joseph Stephan Institute. Focusing on the detection of suspicious behavior and data analysis, Boshan has published numerous articles in professional journals and delivered conference papers. Boshan is now working on his second book, Practical Machine Learning in Java, scheduled to be published later this year. Well, hello, Boshan, and how are you doing?
Hello, Martin. Thank you for the introduction. I'm doing great. I'm really excited to be here today.
Great. So, before we begin, let's welcome all the attendees and thank you for joining us. Now, let's quickly go over today's agenda. We'll start off with an introduction to the main concepts in machine learning and then look at critical challenges facing IT operations analytics. We'll jump into how to use changes as a correlation anchor and the application of causal analysis to help identify root cause. Then we'll follow up with a demo given by our VP R&D, Eyal Oz. Hey Eyal, are you there? Hello, Eyal?
Yes, guys, I'm very happy to be here with you today.
Great.
Talk to you later during the demo.
Excellent. So, we'll wrap it up after Eyal's demo with a dedicated Q&A session. To remind you, throughout today's session, you can send questions using the GoToWebinar control panel located on the right side of your screen. We'll do our best to address all the questions during the dedicated Q&A session after the demo. So, let's get started. Boshan, I'm going to hand this over to you.
Thank you, Martin. So, the topic we'll talk about today is how to leverage machine learning to find interesting insights across silos in IT operations. So one of the main reasons why root cause analysis in IT operations has not seen any progress in the last 10 years is the fact that IT still operates in silos. And this webcomic here illustrates the fact that the data are not stored only on physically separated locations, but they are also separated by information schemas. You see these two guys are discussing, no, these aren't storage tanks, these are information silos for ERP, human resources, payroll, and financial data. Simply use the convenience ladders to access each one. And sadly enough, if we replace these information silos with APM logs, deployments, and change requests, the punchline is still valid. So now to extract the information and to get the full picture across silos, it's really a challenge. And to get to an effective root cause analysis, it's really hard using only a limited view, to looking only into a single silo. What we need to look at cross silos. And obviously, to achieve this, we need to bring all the data together. And not only bringing, but only to understand what is the relationship between them, how these data are correlated, how they affect each other, what are the interesting patterns, insights, and finally, how to identify root causes that appear in cause incidents. And in this talk, we'll look at some examples how machine learning can help with this task. So, first, last question, can machine learning actually help? Well, machine learning has been traditionally used to discover new insights in data. The technology consists of many algorithms that are able to process large amounts of data and find interesting recurring patterns or some other regularities in the data that can help us understand the problem. Systems using machine learning, we can recognize the common situations, and the system can adapt to these specific situations. And besides, IT operation is a really well fitted domain to machine learning, mainly because it has really large amounts of data available for analysis. And given the growing progress of additional risk, not data center energy efficiency and load balancing, or anomaly detection in APN data, workload, and configuration to detect incidents, or even predicting faults in IT centers. So the question is now how to leverage this machine learning to help solve this problem. The current correlation technologies can be basically split into three categories. The first are so-called event correlation engines. These event correlation engines, although the name is quite promising, are mainly focused on event filtering, aggregation, and masking. They're able to bring together different data sources and suppress some events, remove duplicate events, and apply some kind of rules on top of these events. The next approach is event clustering. This is actually quite smart filtering that is able to detect event storms. For instance, if an incident happens, we can see many APM alerts coming from different areas. And with this smart clustering, we can actually collapse these events into a single storm. The third approach is focused on calculating correlation coefficient, which compares two time series and calculates this coefficient. And actually says, okay, these two data sources are correlated, so you can basically collapse one and show only the other. The benefits of these approaches is that they do reduce the number of total events, and which does make life much easier. And when a user needs to manually investigate lots of data, it can speed up the process. But the drawback is that correlation coefficient allows us to identify that two data sources are related, but it doesn't say which one affects the other. And besides knowing that some events happen at the same time, it's usually not sufficient for root cause analysis. And even if we're able to mask events and detect event storms, it only tells us, yeah, there was a huge event, but it still doesn't pinpoint to the root cause. And to actually understand what is the root cause of a problem, to actually answer this question, we need to understand the cause-effect relationship between data sources. So let me explain what I mean by that. When we talk about executing application deployments or infrastructure automation, there are probably some administrators applying manual changes to the system. And we call this IT context. And IT context is basically what introduces changes to the system. Then we have the actual changes that appear in the system, and they cause system to work differently. Because if nothing changes, there is no reason for the system to work differently. And finally, we have symptoms which monitor the impact of these changes to the system. And this could consist of log monitoring, network monitoring, and APM. So basically, we have three different sources of data: IT context, actual changes, and symptoms. And the critical ingredient to come from a symptom, from an incident, to actually the root cause is to look through the actual changes to the system. So almost everything in IT surrounds around changes. On one hand, changes are being planned, changes are being implemented. And on the other hand, performance alerts show the impact of these changes on performance. So they are both a critical ingredient for causal analysis and the basis point for correlation. We call it correlation anchor. So in order to leverage this fact, we can apply the causal reasoning with machine learning in three steps. In the first step, we need to detect the actual changes. The actual changes can happen on many levels. For instance, we can look at configuration changes, capacity changes, code changes, data or workload changes. And besides, we need to understand what is the risk associated with each change. And this is the first place where we can leverage machine learning and use predictive models to actually estimate if a specific change will have a potential impact on the system performance. Then once we have the changes, then we need to correlate all the other data sources to these changes. So we need to correlate the IT context. These are deployments, change requests, and symptoms back to the changes. And here we can use some traditional correlation mechanisms, as we discussed before, or we can leverage machine learning using fuzzy logic, linguistic correlation, statistical models, and so on. And we'll look at a couple of examples later. And the final step is to apply the causal reasoning. And here the idea is to build the actual dependency diagram and to model the error propagation. Okay, and we'll look at the detailed example a little bit later. So let's start with changes. An important step in detecting changes is also estimating the risk of impact to the system performance. And this can be done using a risk tree. An example of a risk tree is presented here, and it can consist of several different areas. The first one is a prior risk associated with particular configuration. This can be in form of a knowledge base when an expert says, okay, I know that this particular configuration parameter in a database is really critical and important. And if it's changed to a specific value or out of a normal range, it could cause issues. The second set of rules could be user-defined, saying, I know that my application works only with Java 8. If this is not Java 8, it could cause issues. Then the third set could be operational risk. For instance, if I see a change on my 3 production servers, but this change is inconsistent, meaning it was applied only on 1 server instead of 3, it could cause operational risk. And then we can have all sorts of other heuristics, which could again use machine learning, like time anomaly, loneliness, and so on. And we can combine all of these aspects of risk into one decision tree that is able to model what is the risk associated with each change. So at the end of the day, when a change is introduced to the system, we are able to estimate the probability that this change will cause an incident. And as we will see later, this is the first important step in the analysis. Now, let's move on to the correlation mechanisms. Once we identify the actual changes in the system, now we want to correlate symptoms and IT context to these changes. Now, the typical correlation mechanisms could include contextual correlation, matching rules, and concurrency. For instance, contextual correlation matches the exact event attributes or correlates by a specific host or environment. Then typical correlation mechanisms include also matching rules. The most frequently used form are regular expressions or rule sets, or a specific example of this is concurrency mechanism, as we saw before. For instance, if we see a couple of events happening at the same time, we just collapse these events and identify them as an event storm. Now, advanced mechanisms based on machine learning apply when we are not able to do the exact matching. And when we work with many data sources, we need to deal with uncertainty. So we need to introduce approximate matching, such as fuzzy logic or linguistic correlation, where we try to identify some keywords corresponding to particular environments, or statistical correlation, where we model how actions affect the system. And further on, a causal correlation, where we need to leverage the context to model dependency. So now, in the following slides, we'll look at 2 examples, how, for instance, machine learning can be used to implement linguistic correlation or statistical correlation. In linguistic correlation, the main idea is to identify topics in describing a particular environment. Let's say an MS SQL server. The idea is that we look at this environment, take all the configurations in this environment, and try to extract interesting keywords describing this environment. And we can use an algorithm called latent Dirichlet allocation that is able to transform this particular configuration into a vector space model and extract keywords that appear in MS SQL Server but do not appear in other environments. So this way we get a topic for specific environment. And once we see an APM alert, we can track these keywords and try to establish a match between specific environment and specific APM alert. Another approach based on statistical correlation could look into how to create a model about how system responds to changes. So we basically have an IT action, let's say deployment, change into the system, let's say update to my application, and the typical symptom. And this triplet can be used to model the typical cause-effect relationship based on historical data. And an example of implementation could be based on deep convolutional neural network that models short-term and long-term influences of changes. So when we see a triplet IT action change symptom, we want to understand how the symptom will appear after a change will be introduced to the system. Now let's move on to the causal reasoning. The main algorithm for causal reasoning is Bayesian belief network. Here I have an example how Bayesian belief network could be used to make causal inferences about the problem. For instance, we can have automatic deployment or execute a change request which could cause an incident. And the incident could be observed as a log error as an APM alert. And then in the next step, we assign probabilities of this event. For instance, to automatic deployment, we assign probability 0.02. To execute a change request, 0.001. Then we say, okay, suppose that we see an incident, we can say what is the probability of incident given that we just executed automatic deployment and executed a change request. And we can assign probability for combination of these two events. Suppose this is 0.16, which means that in 16 out of 100 times there was an incident when both events happened. And similarly, we can say, okay, what if only automatic deployment happens? What if only change request happens? What about if nothing happens? We can still have an incident, which could be caused by an outside cause, maybe a disk failure or something like that. And then in the next step, we model, okay, now I suppose we see a log error. What is the probability of incident? If there was really an incident, did we really see a log error? We say yes. Every time there is an incident, we definitely see a log error. But what about when there is no incident? Well, we still see many log errors, but these are actually noisy errors. So when we see an error in the log, it could mean that there was an incident or it wasn't. And we can see that these log errors are quite noisy. And similarly, APM alerts. When there is an incident, APM alert surely catches it. But there are many times, when we see many APM alerts when there is no incident. And once we define a network such as this one and define the initial probabilities, then we can start asking interesting questions. Now suppose we see two errors, log error and APM alert. And we know that no deployment or change request is observed. Now what is the likelihood that we are dealing with an incident, given that we see two error and alert? And you can use this network to reason and calculate that the probability of an incident is only 5%, because we see no automatic deployment, no change request, and the probability of an incident in this case is very low, 0.1. And on the other hand, we know that the log errors and APM alerts are quite noisy. Now, suppose we have another example. We just executed the change request, and now we see a log error. What is the likelihood that we are dealing with an incident? And we can simply update these probabilities and see that the probability of incident is now more likely. Although we see log errors many times even when if there is no incident. And similarly, let's say we execute a change request and now we see a log error and APM alert. Now in this case, the likelihood of incident is really high. So we can really start an investigation. So this is really a simple, small-scale example to illustrate how reasoning with Bayesian belief network works. What we do in reality, we use the environment dependency diagram to build a much larger Bayesian belief network. And we can use forward reasoning. For instance, if a change was introduced in the system, we can track how this change will propagate the system, how the impact of this change will propagate to the system. And on the other hand, we can do the backward reasoning. For instance, if we monitor the impact of a change on a specific component, we can track back what is the most likely root cause causing this impact of the change. So we can then quickly navigate back and forth and estimate what is the most likely root cause at each step. So, in summary, to do an effective root cause analysis, we need CAUSAL perspective. And the key ingredient is to leverage the context in the data. And we see that this key ingredient are changes, which can be seen as a correlation anchor and is a critical ingredient for causal analysis. And finally, the correlation could be advanced with machine learning. And so we quickly overview a couple of examples how to use linguistic correlation, statistical correlation, and finally causal reasoning with Bayesian networks. So this concludes my presentation, and Eyal will show a couple of examples how this is achieved in practice.
Okay, thank you very much, Bayezian. That was really interesting and thought-provoking. I'm going to hand over the controls to Eyal, and he will continue with the demo.
So hello, everyone. I'm very happy to be with you today. So thank you very much, Bayezian, for this presentation. Now, the good thing about everything that Bayezian explained is that eventually when we build the UI around it, you don't need to understand all the algorithms behind the scenes, and you don't need to understand all the way the actual algorithms work. All you need to do is to do some point and clicks, and everything will work for you. So let me start by showing what we have today, actually taking everything that Bayezian explained and actually packaging it in the Evolven UI. So what you currently see the Evolven UI actually monitoring the last week changes over on-demand loans, which is like my service system. Now I'm taking my service system and I'm monitoring it, for changes. Now during my work, I actually track a few things. Obviously, the most important thing, as Bayezian explained, are the changes. All these bars, the colorful bars with the yellow, green, and red bars, are the changes. This is actually how many changes happen during a specific time. On the top of this graph, what we see the service desk actions and activities. So every service desk activity is actually recorded in Evolven as one of these purple bars, and this bar is actually grabbed from the service desk system and blended here into this view. This specific bar is CR 4328, which implement a key enhancement reported by customers on my on-demand loans system. Underneath it, what I see in the blue lines, I see actually the release automation events. So in many organizations, not only that we have the service desk to actually explain and open a ticket that says, you know, I have an open ticket from March 12, 8:30 until March 12, 10:30, so I have a 2-hour change period, but I actually have a release automation tool that actually started working and actually deployed a new build. And you see exactly when it started and when it ended, and it's correlated with the time of the service request itself. On the bottom of this graph, we see two more very, very interesting lines. The first are all the APM alerts that are coming from my system that relates to this on-demand loans system. So we see here that there is one alert calling, saying that the transaction performance is slower than expected. It took more than 15 seconds, which was my goal, and I didn't want to have a transaction which is running 15 seconds. And in addition, I have my infrastructure monitoring solution that actually yelled and said that there is a problem with the low disk space on a specific host. So how do we use all this wealth of data that we have here? So a very simple thing that we can just do, we can just click on the elements. And when we click on a specific element, let's for example click on this element, it will automatically correlate all the changes underneath it. If we go and click on an event that actually has a lot of changes correlated to it, it will not only correlate the changes, but it will also correlate, as you can see here, the actual events that are related to it. So here we have all the three ingredients that Bustian explained earlier. We have the changes in the middle, we have the IT context on top, and we have on the bottom side, we have all the symptoms that are reported by my monitoring tool. Now, everything that you need to do in order to actually do all the fancy algorithms and smart stuff that we are doing behind the scene is just click on a specific event. And when you click on this event, which is, as I said earlier, a low disk space in one of the specific hosts, what the system actually does, it actually goes, correlate using the algorithms that Bustian described earlier, and it correlates the changes to the specific event that we see here. Now, when we look at these changes, we can go and see that I have here 3 changes, and I have here an additional change, which is a total of 4 changes. But I don't need to go and look only here. I can go and drill down on to the details. So I see that I have 4 changes in my Tomcat environment. I see that most of them are high risk. One of them is medium risk. And I see that all these 4 changes are inconsistent. When I'm looking on these 4 inconsistent changes, I can see that these 4 inconsistent changes are actually these 4. And one of the things that actually just popped to my eyes immediately is this one, which actually is very suspicious, because it actually took the log level on the Tomcat system and moved it from info level into debug level, meaning it's now suddenly taking a lot more disk, and my logs are occupying a lot more disk than what I expected earlier. And this is probably the cause of this alert, and that makes everything here slow, because the system is actually starving for disk space, and the disk space is very, very low. So this is one example of how the correlation works in Evolven, and how to just actually manipulate it and just use it using a live system. So that was a very, very short demo that I wanted to show. So Martin, back to you, and maybe we have a few questions.
Okay, thanks a lot, Eyal. I'll just take back the controls here.
Okay, thank you. So do we have any questions?
Yeah, we have a few questions. Some of these are for you and some are for BAYESIAN. BAYESIAN, can you tell us
Yes.
why are changes so important?
Okay, first, if nothing changes, if the system wouldn't change, there would be no problems. What do I mean by that? If you have something that works constantly, with the constant input, it will produce the constant output. But now we have several options when the output changes. Either the input changes, that means that the input distribution is different, that means that we have a change in the workload, or the configuration of the system changes. And by configuration of the systems, that means codes, capacity parameters, and stuff like that. And if everything remains constant, there is no reason for the output to change. So the only reason for output to change is to actually change something into the system. So from this perspective, everything is traced back to the changes in the system.
Okay. For Eyal, you mentioned some different data sources. Would I need all the blended data feeds integrated in order to get value from using Evolven?
Actually, no. Actually, Evolven works really, really fine with only a few of these data sources integrated, or even without any data source integrate at all. The only thing that these data sources are actually adding is, as we understand, the IT context and the symptoms. Now, if, for example, I do not have my IT context integration, so I don't have service desk integration, and I don't have my release automation integration, and I only have my APM tool integrated, then I will only see the alerts emitting from the APM system in my graph, and clicking on this element, on this alert, will actually correlate with the existing data that we already have. Now, inside Evolven, assuming that you do not have the service request, service desk integration, you can manually enter these events if you want, or you can add just rules. For example, in many organizations, they have rules saying deployments are only allowed during between midnight and I don't know, 2 a.m. So these rules can apply into Evolven without the need to do the actual integration with Service Desk. This is obviously less powerful, but nevertheless, you still have all the capabilities of correlating the alerts to the changes.
Okay, thank you very much, Eyal. We're wrapping up here. So I'd like to thank you all for taking the time to join us for this session. I personally found this to be very interesting. And you should know you can feel free to drop BAYESIAN a line with any questions or feedback, or contact us to schedule a one-to-one demo of Evolven. So on behalf of all of us, I want to thank you all for taking the time to join us today. Thanks again, BAYESIAN and Eyal.
Thank you, guys. Thank you for everyone. Thank you, everyone.
Thank you. Bye.